Hey everyone, welcome. Today we're tackling a Leetcode problem called Count the number of arrays with k-matching adjacent elements. It sounds a little complex, but don't worry. We're going to break it down into simple, easy-to-understand pieces. Let's get started. Alright, so here's the task. We're given three numbers, a length n, a maximum value m, and a count k. We need to figure out how many different arrays we can build that follow three rules. First, the array has to have length n. Second, every number in it must be between 1 and m. And the third rule is the most important. There must be exactly k places where a number is identical to the one right before it. Let's walk through an example to make this concrete. Here, the length n is 3, the numbers can be 1 or 2, and we need exactly one match. So how do we get 4? Well, let's think about where that single match could happen. It could be between the first and second elements. So the array would look like x, x, y pret. Since the numbers at the first two spots match, the third number must be different, otherwise we'd have two matches instead of one. If x is 1, then y has to be 2. That gives us the array 1, 1, 2. If x is 2, y must be 1, giving us 2, 2, 1. That's two arrays already. What if the match is between the second and third elements? The structure would be y, x, x. Same logic. If x is 1, y must be 2, giving 2, 1, 1. And if x is 2, y must be 1, giving 1, 2, 2. And there you have it, two possibilities from the first case, two from the second, for a total of 4 arrays. Okay, so what's the first idea that pops into your head? For most of us, it's probably let's just build every possible array and count the ones that work. But if n and m are large, the number of arrays would be enormous. That approach would time out for sure. This hints that we shouldn't actually build the arrays. We need a more clever way to count them. This is a classic sign that we should be looking at a mathematical or combinatorial approach. So let's rethink this. Instead of building the array from left to right, let's think about its structure. We can actually break the problem into two separate, independent decisions. First, we decide where in the array our k-matching pairs will occur. Second, once we've picked the locations, we decide what numbers to fill in to satisfy those match and mismatch conditions. If we can figure out the number of choices for step 1 and the number of choices for step 2, we can just multiply them together to get our final answer. Let's focus on step 1, choosing the positions. An array with n elements has n1 adjacent pairs. For example, if n is 5, there are 4 spots where a match could happen. Our job is to pick exactly k of these n1 spots to be our matching pairs. This is a standard combinatorics problem. The number of ways to choose k items from a set of n1 is given by the combination formula, which we often write as n-1, choose k pairs. Now for step 2, assigning the actual numbers. All those matches and mismatches effectively chop our array into segments of identical values. If you think about it, every mismatch acts like a wall, starting a new segment. So k matches and n1k mismatches will give us a total of nk segments. So how do we color these segments? For the very first segment, we can pick any of the m available numbers. But for the second segment, its value must be different from the first one, so it only has m1 choices. This pattern continues for every following segment. Each one has m1 options, because it just has to be different from the segment right before it. Now let's put it all together using the multiplication principle. The total number of good arrays is the number of ways to choose the positions, which we found was n-1, choose k prod, multiplied by the number of ways to assign the values. For the values, we had m choices for the first segment, and m1 choices for each of the other nk1 segments, and that gives us our final formula. It's the combination part, multiplied by m, multiplied by m1 raised to the power of nk1. Alright, here's the full Python code that implements our strategy. I know it might look like a lot at first glance, but don't worry. We're about to walk through the key parts, step by step, to see how it matches the logic we just discussed. Before we can use our formula, we need a couple of helper tools. The init function here is for precomputation. It calculates all the factorials we might need, up to the maximum possible value of n. It also computes their modular inverses, which is a clever math trick for handling division when we're working with these large modulo numbers. This lets us calculate the n choose k part very quickly later. And that qpow function is just an efficient way to calculate powers, which we'll also need. Okay, here's the heart of our solution. This is where we use our formula. First, we calculate the combinations part. We call our helper function c to find n-1. Choose kpolv, using those values we pre-computed earlier. Next, we calculate the value assignments part. This is m multiplied by m1 raised to the power of n1k. Notice we use our fast power function QPOW for this. Finally, we just multiply these two results together. Take the modulo one last time to keep the number in range, and that's our final answer. So how much better is this than brute force? It's way faster. The time it takes is dominated by the one-time precomputation step, which is proportional to the maximum possible size of n. After that, each calculation is super quick, mainly involving the power function, which is very fast. For memory, we do need to store those pre-computed factorials, so the space we use is also proportional to the maximum n. This is a fantastic trade-off for the massive speed-up we get. So let's quickly recap the main ideas. The big win here was breaking down a complex counting problem into two simpler, independent parts, choosing where the matches go, and then choosing what values to use. We used the classic combination formula for the where part. And for the what part, we simplified the logic by thinking about the array as a series of segments. By putting these two ideas together with some efficient precomputation, we found a clean and very fast solution. I hope that explanation was helpful and made sense. If you found it useful, I'd really appreciate a like on the video, and maybe subscribe for more breakdowns like this. If you have any questions or a different way to solve it, drop a comment below. And hey, if you're feeling extra generous, there's always the Boba Fund. Thanks for watching, keep up the great work, and I'll see you in the next one.